Lesson 4 starts off with a review of the summary of transformations. This covers every type of transformation that you studied previously in Math 107 or whatever course you had outside of GCC if you tested into the class. This will be the type of sheet that you'll be referring to probably over and over again. Again, anything that's horizontal, whether it's a horizontal shift where you're moving it right and left on your number line, or up and down your, or shrinking it or compressing it, is always counterintuitive. It's the opposite of what you think it is. So that's the kind of thing to remember. So when you see something like this, and horizontal has to do with input. Your horizontal variable is inside those parentheses. So when you see this 3x here, that's actually shrinking it by 1/3, not making it bigger. Okay, so it's the opposite of what you think. Okay, so this whole idea, 2, 3, and 4, has to do, all three of these questions has to do with today's topic, which is inverse functions, whether something is invertible. That's another way you can say it. H is invertible, means the function h has an inverse function. Okay, so one of the things we notice about inverse functions is that if you switch the x and y components, okay, then you would get a function as a result. So if we switch these components, let's take a look at them. We have -2, 4, -1, 1, 1, 1, and 2, 4. So if we switch, all right, enough, Rob, come on. If we switch the components, the x and y's, on these ordered pairs, the question is the result a function? And I hope you answered no, because you see here that one has an identity crisis, right? One doesn't know who they are. In one pair, it's -1, and another pair, it's +1. So this is a relation, okay? It's not a function. Any set of ordered pairs is a relation. So I should have my set stuff out here. Any set of ordered pairs is a relation, with the special condition that for each input you have one and only one output. That makes your relation a function. Okay, so this says to solve for y. So this is basically a little algebra work where when you solve this for y, you're really finding an inverse, and we'll talk about that ad nauseum in about 3 minutes. So to solve for y, you first are going to subtract 4 from each side, and anytime you do that, anytime you get more than one term on the side of an equation, you should always put it in parentheses, because any act you do to that expression has to apply to both terms. So now you have a proportion. Okay, you can either see this like this. I'm always going to try to bring this up when I can, because we're so weak with proportions. AD will equal BC. So you can just multiply x minus 4 times y, and that equals, and what's hidden right here on the bottom? 1. 1 times 5 is 5. Or you could just say, I'm going to multiply both sides by y. They both bring you to the same spot. Okay, and now we want to solve this for y. So the coefficient, and this is probably a different way that you're not used to seeing this, the coefficient of y is x minus 4. A coefficient, you're always just used to thinking about coefficients like 3 times y or -4 times y. A coefficient is any factor that multiplies the variable of interest here, right? So x minus 4, you have x minus 4 y's. So to solve for y, you divide both sides by the coefficient. And now you've taken that equation in terms of x, and you've now solved for it in terms of y. So the language that we use between these two different equations is we say this first equation is solve for x in terms of y. This one is solved for y in terms of x. So often we'll be starting off with this type of function, and we'll be asking to find the inverse, and we're going to work our way back to this type of function as the inverse. So when you look at a function like 5 divided by x minus 4, you have two transformations that have gone on. Can anybody recognize what the toolkit function is, the parent function for this one? 1 over x, right. So if we say f of x equals 1 over x, and we call this g of x, then what's happened to 1 over x? Well, the whole thing, if we want, on the outside has been multiplied by 5. 1 over x has been multiplied by 5 because you have a 5 in the numerator, which means it's being vertically stretched by a factor of 5, and it's had horizontal shift to the right 4 units. Okay, so if you wanted to get a quick graph of this, hopefully you know from your toolkit functions what the reciprocal function looks like. You stretch everything and then scoot the whole thing 4 units to the right. That's using your transformations. Also, having a picture of what this looks like, you know that your reciprocal function, which looks like this, oops, it's not supposed to touch the x-axis, gets really, really close. All right. Your reciprocal function, okay, and it's not supposed to touch the y either. All right, it's just my pen. So we know what if we stretch that or scoot that left or right, it's still going to be 1 to 1. Why am I even concerned about 1 over x being 1 to 1? Why would I be concerned about this function being 1 to 1? Nobody remembers? I can't hear you. You're mumbling. Pondering. Why do we even care if a function is 1 to 1? Right. If a function is 1 to 1, that means it passes the horizontal line test. Then it has an inverse that's also a function. So we know that this has an inverse that's also a function. Okay. So that's a little more than what your preview exercises asked you to do, but that's the type of thing that we're leading into today. All right. Did someone have a question for 4 or just 3? I think it was 5 we had a question on, right? Yeah. Okay. Where's the typo? Oh, thank you. Thank you very much. I'll do that after. Okay. There can never be 2 functions. Please, those of you who are like editors and you find these, let me know so I can fix them for the next time I teach the class. There can never be 2 functions, f and g, where if f and g are not exactly the same function, then when you compose them, f of g of x and g of f of x, they equal each other. And someone says it's not true, and that's the correct answer, because the one situation where this is true is when f and g are inverses of each other. If f and g are inverses of each other, you come right back to where you started. So this is false, and you can say true when f and g are inverses of each other. This is the only time that composition of functions is commutable, the commutative property, where you change the order and it doesn't matter. You have the same result. Okay? So in this case, if they are inverses, then you can write this type of thing. In fact, this is the only way you can prove that 2 things are indeed inverses of each other. You must compose them and get x out as a result, and then you have to compose them in the reverse order and also get x as a result. Okay, so this basically is like a round trip. Wherever you start, you go off, you come back, you're right back to where you started. And no matter which order you do that. you would be right back where you started. Okay. All right, so let's take a look in more detail at inverses and do a little work with them for those of you it's been a while since you've had inverses. So here are two functions. F of x equals the x cubed plus 1, and g of x equals the cubed root of x minus 1. Now, these two functions are inverses of each other. I'll tell you that right off the bat. However, if you wanted to prove this to me, or you didn't know that they were inverses, this is what you must do. You must compose them and then reverse the order of the composition, and the final result here has to be x. Okay? So let's quickly review. If I gave you x cubed plus 1 as a function and asked you to find the inverse, how would you do it? Does anybody remember the process we go through for finding an inverse? Right, so right now this says y equals x cubed plus 1. Okay, so you flip-flop x and y, so you put an x here and you put a y here. Because basically we're trying to undo everything that happened to x. X gets cubed and then 1's added to it. So to undo that, you solve this now for y. So if I asked you to undo what's happened to poor old x here, the first thing you would undo is adding 1 to each side. So you would subtract 1 from each side, right? That would be the first thing you would do to undo it. And then x is cubed. So to undo x, you would cube root each side. So now you cube root each side, and you're back to y. And this, now you call y f inverse of x. And we use this little -1 to symbolize f inverse. It doesn't mean take the reciprocal or anything like that. Right? So finding inverse functions is undoing each step that's happened to your original x. Okay, and before I even start, in my mind, I think, what does x cubed look like? My toolkit function says something like this. And then x cubed plus 1 shifts up 1 unit. I know it's 1-to-1. I know it has a function. So these are all the types of things that should be going on in your mind as you consider whether something has a function, an inverse or not. Okay. All right, so this is just saying take the two compositions here. So where we see g of x, we're going to replace it with what? Where we see g of x right here, what are we going to replace it with? Right, we're going to replace it with what g of x is right here. So we're going to put in here the cubed root of x minus 1. That's the first thing I do. And now this g of x, this whole thing here, is now my input into the function. That's my input. So now I look at f and I say, what does f tell me to do to any input? F tells me to cube my input being the cubed root of x minus 1. I'm going to cube it and then add 1 to it. And now cubing and cube rooting are inverses of each other. They undo each other. And I'm left with x minus 1 plus 1, which gives me x. So you got half of a smiley face, because you're halfway home to proving that those are inverses of each other. You're not there yet, but it's satisfied the first composition that they undid each other, and you're right back to where you started, because you started right here with x, you did all this baloney to it, and you're right back to x. So now to prove it, you have to show you have to reverse the order of the composition. So now what's going into our g function? What's going into our g function is f of x. So now your input is f of x. So f of x is x cubed plus 1. Okay, x cubed plus 1. So now you say, what does g do to anything? G says whatever your input is, take that input, subtract 1 from it, take the input, subtract 1 from it, and then cube root the whole thing. So now my input is this x cubed plus 1, this red x cubed plus 1. So I'm going to take the cubed root of my input, which is x cubed plus 1, and I'm going to subtract 1 from it. So that's the cubed root of x cubed, because the 1 and the subtraction of 1 bring me to 0, and the cubed root of x cubed is x. So now I have the other half of my smiley face. Okay. So that's how you show that two functions are inverses of each other, and it's the only way you can show it. Now, when someone says, well, what if I did a number like 2, and I put 2 in here, and I got 9, and I put 9 in here, and I got 2 back again? Does that prove it? No. It only shows that that works for one number. And you have to show that it works for all numbers in the domain of your function, which in this case right here is all real numbers. So you've got to show it for all x's. Okay? Any questions on that? That's like a big idea from college algebra, how to show that something, two functions are inverses of each other. Anybody? No hands? All right. So here are some basic facts about inverse functions. These are the types of things that, you know, we end up summarizing at the end of a couple of days in 107. We know that a function has an inverse only if it passes the horizontal line test, because it means it's 1-to-1. What's the most famous function probably that doesn't have an inverse that you always want to have an inverse? X squared. That's sort of the killer, right? In the sense that your parent function x squared, because we think of the square root as being undoing a squaring, what we forget is that this has two sides to it. It has the negative square root and the positive square root. So when you square root both, whoops, when you take the square root of x squared and you do this, that's incorrect. Because we don't know whether x is positive or negative, so that's why you have to do this. All right, so you can see the horizontal line test is really going to mess with your mind a little bit, because if you were -3, you'd come out and be 9. And if you're +3, you come out and you're 9. It's not 1-to-1. So if you put 9 into your inverse function and square root it, you get 2 answers. And that's not a function. So the only way when you have an even function, that means a function that the horizontal line here is going to, well, there's several different ways for even functions. Here's when a function is even. This property always holds true. So if we're looking at x squared, here's f of x. It's x squared. If we put in the opposite of x and square it, guess what? We come right back to x squared. So that tells us that this function is even. It has symmetry about your y-axis, and therefore it doesn't have an inverse that's a function. So the only way you can create an inverse is what we did in number 4 in the preview exercises, is you can say, I can find the inverse of this function if I restrict the domain. If I say x is greater than or equal to 0, voila, I have an inverse. It's called the positive square root of x. If I say x is less than 0, voila, I have an inverse, the negative square root of x. That's the only situation that you can possibly have an inverse function when you start off with x squared, is you have to literally wash away half of the graph. If you wash it away, erase it away by changing your domain, then you have an inverse function. Okay, that's number 1. Number 2, so ordered pairs switch with inverse functions. So let's just look at a very simple example of two inverse functions. Here's x plus 3, and the inverse is x minus 3. So if you looked at some limited numbers of ordered pairs here, let's say x is -1. Here we're looking at the function f. Then y would be 2. And if x is 0, y would be 3. And if x was 2, y would be 5. Let's just take a look at those three ordered pairs. Those are 3 points that are solutions to this function right here. Now, what's true is that the domain and range of inverse functions swap. That means the output for your first function becomes the input into your inverse function. So when I put 2 down here into my inverse function, I'm right back to -1. See, they just swap places. That's always true. So if you were asked to find f inverse of 5, f inverse of 5, this is, and you don't have a graph, you just have 2 equations. You say, okay, 5 is the input in my inverse function, which means it was the output of my original function. So then you would take this original function and you say, when does x plus 3 equal 5? When x is 2. You set this equal to 5, x is 2, so that's the answer to your inverse function. Inverse of 5 is 2. And you can see that they swap places, 5, 2, 3, 0. So that's what that language means. And number 3 is exactly the same thing as number 2, except for we've put that information in terms of domain and range. Number 5 is what we just talked about in number 1, that when you reverse the order of the composition, you come back to where you started. And if you had a graph and you had a very limited graph and you wanted to draw the inverse, then your inverse function is symmetric over the line y equals x. So for example, if I just did some kind of quick piecewise function right here like this, let's see, let's suppose it started at 0, 0, and then it went like this up to 2, 2, and then it went like that up to, I don't know, what's that look like, 5, 4, and I wanted the inverse of that. Some people can do this right away with their thinking. You take the line y equals x, and then you just create the point that's on the other side of that line. And the way you do that is you switch the x and y's. Okay, I should make this 2, 3. So 0, 0 stays where it is. 2, 3 becomes 3, 2. And 5, 4 becomes 4, 5. So the inverse would be like that. You just swap the x's and y's. And that, if this was done to scale, this would have perfect symmetry about the line y equals x. All right, that's about as fast a review of inverses from 107 as I could possibly do. All right, so now we're going to start this. I'm sorry that this started at the bottom of one page. Did it, or you got it all on one page? Do you have it all on one page? Oh, good. Okay, good. So when I guess when I created a smart notebook, it put this on the bottom. Okay, so I decided to start not with a simple function to find the inverse of. And it's even a little harder than the one we just did in the preview exercises. So I might as well start with one. We used to do this type of function. There's another typo there. Did you catch that one, Hazel? No. We used to do these types of functions in 107, and they were just more of a, I think at the 107 level, you're just trying to get all the ideas down for inverses and finding them without too much algebra. But what you're going to find out in calculus is that your calculus class goes much easier the better you are with algebra. There's just a lot of algebraic, like, kind of skills you have to use over and over again in calculus. So first of all, check to see that this is 1-to-1. Now, what I did, I mean, I know what this function looks like, or I have a general sense of what this function looks like, but if I didn't, I would just pop up GeoGebra or Desmos, or if you have a graphing calculator, and I throw it into my graphing calculator. So what is that function? It's something called a rational function, which we're going to cover in maybe a week or so. And you just want to make sure that when you look at a picture of this, that it is 1-to-1. So what is our function? Is it 2x plus 3 over something? Okay, thank you. Okay, so f of x equals, and I use parentheses, 2x minus 1, and because I haven't put anything else in, it's drawing a line, divided by, and what is it, x minus 3? Oh, thank you, thank you. Okay, so there you are. This is what a rational function looks like. So what you're going to be learning shortly is that there's this vertical line that comes down through -3, because -3 is not in the domain, because it would make the denominator 0. So really kind of funky things happen as you approach that -3 symbol. So let's scoot out so you can see this. Woo! All right, so that's what the function looks like. Is it one-to-one? Yeah. So you know you can proceed now and go on to find your function, your inverse function. All right, so let's take a look at that. So like I say, you do one or two of these and then they don't bother you too much in terms of the algebra. You get used to it. All right, so we're going to replace f of x with y. So now it's going to, the first step is y equals 2x minus 1 over x plus 3. So I just take f of x and replace it with y. And now because I know my x's and y's swap places with inverse functions, I'm just going to swap the two variables right now. X equals 2y minus 1 divided by y plus 3. And now you're going to solve the new equation for y. So when you do this, you're undoing everything that originally happened to x. That's why you do the swap now. All right. You say to yourself, oh, I have y's in both my numerator and denominator. So the first thing you have to do is you want to create an equation where you have not a numerator and denominator. You want to sort of make it look more linear type function. So again, your cross products, your proportion says x times y plus 3 equals 2y minus 1, or you can multiply both sides by y plus 3, whatever you want to do. So you will get a statement that looks like this next. So now notice you've got y's on both sides of your equation, and the poor y that's on the left-hand side is kind of like cornered. It's in jail. It's not free yet to move from one side of the equation to the other. So the next thing you have to do here is you have to use your distributive property on the left-hand side. You get x times y plus x times 3. And on your right-hand side, you can drop those parentheses and you won't get into any trouble. 2y minus 1. Okay. So you have two terms on the left-hand side and two terms on the right-hand side. And you want to get all your y's on one side of the equation because you're trying to solve for y. And it doesn't matter which side you bring things to. So again, I want you to see this, that this y has what for a coefficient? How many y's do I have? X of them, right? So in your mind, just think of this as like 5y or 2y or whatever. You're going to just move it from one side of the equation to the other. So I'm going to subtract xy from both sides of the equation. And at the same time, I think it's okay if I do this because we're in 108 now. I'm also going to add 1 to both sides. Is that okay for me to do both steps at once? If not, let me know. So on the left side, I'm going to have 3x plus 1. And on the right-hand side, I'm going to have 2 times y minus x times y. You're almost home. The last step is staring at you right in the face. And what's your favorite form of factoring, Shane? No. G what? Greatest common factor. Do you see something staring at you in the face on the right-hand side? Yeah, that y is a factor common to both of those terms. So, and this is really what you do, folks. We just never show you this because we're so used to just working with numbers. If this said 2y take away 5y, what would you do? 2 take away 5, and you'd put the y after it, right? So you're combining these terms by subtracting 2 take away x. But for many of you, it's just easier to think, I'm pulling a y out. I'm factoring out a common factor. So 3x plus 1 equals y times 2 minus x. It does. Now you want to solve for y. You divide both sides by the coefficient, which is 2 minus x. And voila, your job is done. So 3x plus 1 over 2 minus x is the inverse function. You do that a couple hundred times and you won't even think about it again. Now I'm being silly. You do it 3 or 4 times, you're going to get the hang. Oh yeah, I got to get both y's on the same side. Oh yeah, I got to factor out the y. And then it comes right back to being another rational function right here. Okay? Which you should expect. If your original function had an x in the numerator and an x in the denominator, you might expect that your inverse function is going to look in a similar form. Okay? So again, all the steps are done here for you. I would suggest that later on you're going to have lots of time now to work on your inverting for your lesson activities. So you'll have quite a bit of time to work on this procedure. Okay? Anything before you go on to your lesson activities in the back of your mind? Anything? Okay. So this is section 1.4. So the homework you'll have tonight will be for section 1.4 in the book. Now, I also want to point out that your more practice exercises has tons of problems for transformations. All those, anything from section 1.5 is going to be transformations. So if it's been a while, or even if you've had 107 and you're a little shaky with transformations, this might not be a bad idea to do some of the more practice problems as well. Okay? All right.